Imagine you are standing outside tonight. No city lights, no noise, just you and the sky above you, that ancient, familiar ceiling of stars that human beings have looked at for 100,000 years. You tilt your head back and you see it the way your ancestors saw it. The Milky Way cutting across the darkness like a river of frozen light. Constellations that sailors used to navigate oceans. Stars that poets wrote about. Lights that feel safe because they have always been there. Now pick one patch of sky. Any patch. It doesn't matter which one. Hold your thumb up against it and cover a small section of stars. Just a little square of darkness between the lights. What you are looking at in that small square, in what appears to be empty, harmless space between stars that have human names and mythological stories attached to them, is a black hole. It is not theoretical. It is not a model or a prediction or a scientific estimate. It is a real black hole, confirmed by some of the most sophisticated astronomical instruments ever built, sitting in our cosmic neighborhood at a distance so close that the word close requires you to completely reframe what that word means when you're talking about the galaxy we live in. And we found it in 2022, not decades ago, not in some archive of old data. 2022, 3 years ago. We did not know it existed before then. It was invisible to every telescope, every survey, every sky mapping project in the history of astronomy. It sat there in the darkness between the stars you can see with your naked eye, completely silent, completely hidden, and completely real for billions of years while we looked directly at it and saw nothing. Its name is Gaia BH1, and it is 1,560 light years away from where you are standing right now. Stop for a moment and let that number settle, because your brain is about to try to minimize it. Your brain is going to process 1,560 light years and file it under far away and move on. That is the wrong response. Here is the right one. The Milky Way galaxy, the galaxy we live in, the galaxy that contains our sun and our solar system and every star you have ever seen with your naked eye, is 100,000 light years across. 100,000. Gaia BH1 is 1,560 light years away. In galactic terms, that is not far away. That is not even in the next neighborhood. That is essentially the next street over from where you live. And we had no idea it was there. But here's the problem. Gaia BH1 is not alone. 6 months after the discovery of Gaia BH1, astronomers using the same detection method found another one, Gaia BH2, slightly further, 3,800 light years away. Still, by galactic standards, absurdly close. Still in what astronomers call our local neighborhood of the galaxy. 2 black holes, found in 2 consecutive years, both in our immediate cosmic vicinity, both completely undetected by every previous sky survey. And this is where the real question arrives. The question that the press releases and the academic papers mention quietly, almost as a footnote, but which should be printed in enormous letters on the front page of every newspaper on Earth. If we only just found these 2 in 2022 and 2023, using a detection method that only became possible with the European Space Agency's Gaia satellite, how many more are out there that we haven't found yet? The honest answer from the scientists who discovered them is not reassuring. Based on current models of stellar evolution and black hole formation in the Milky Way, our galaxy should contain somewhere between 100 million and 1 billion stellar mass black holes. That is the scientific consensus. Between 100 million and 1 billion black holes distributed throughout the galaxy we live in. We have directly confirmed the existence of a few dozen, which means the vast majority of the black holes that share this galaxy with us are invisible, undetected, and silent. They do not glow. They do not emit radio waves we can easily detect. They are not consuming nearby stars in a way that makes them visible. They are simply there, in the dark, between the stars, perfectly hidden. Gaia BH1 and Gaia BH2 are almost certainly not exceptions. They are almost certainly just the first 2 members of a population that surrounds us on all sides and that we are only now, for the first time in human history, developing the tools to see. Stay with me, because this gets significantly worse before it gets anywhere close to better. Before we go further into what this discovery means, you need to understand exactly what Gaia BH1 is. Not what a black hole is in the general textbook sense that you have heard 100 times. What this specific object is how it behaves, what it does to space around it, and why the fact that it exists 1,560 light-years from Earth is not a fact you should be able to process calmly. Gaia BH1 is what scientists call a stellar mass black hole. This means it formed the way most black holes form. A massive star, many times larger than our Sun, burned through its nuclear fuel over millions of years, and when the fuel ran out, the star's core collapsed under its own gravity in a fraction of a second. The collapse was so violent and so total that not even the atoms themselves survived. The protons and neutrons and electrons that made up the star's core were compressed beyond any state of matter we can recreate in a laboratory, past the point where physics as we normally understand it applies, into a singularity, a point of essentially infinite density wrapped in a boundary called the event horizon, beyond which nothing that crosses it can ever return. In the case of Gaia BH1, the mass of this collapsed object is approximately 10 times the mass of our Sun. 10 solar masses compressed into a region of space smaller than a city. The event horizon of Gaia BH1, the point of no return around it, has a radius of roughly 30 kilometers. 30 kilometers. You could drive across it in 20 minutes on a highway. But the gravitational effect of those 10 solar masses packed into that space extends far beyond 30 kilometers. Gravity falls off with distance, but it never reaches zero. The gravitational influence of Gaia BH1 extends across a region of space that encompasses its companion star, a Sun-like star roughly similar to our own, which orbits the black hole at a distance of about the same as the distance from Earth to the Sun. 1 astronomical unit. That companion star takes about 186 days to complete one orbit around Gaia BH1. Think about what that means visually. Imagine our solar system, remove the Sun, replace it with a black hole 10 times the mass of the Sun. Then imagine Earth orbiting that black hole at exactly the same distance Earth currently orbits our Sun. That is approximately the scale of the Gaia BH1 system. The difference is that where our Sun provides warmth, light, and the energy that makes all life on Earth possible, the equivalent object in that system is an invisible gravitational drain that curves space-time around itself and devours anything that comes too close. But here's the problem. Gaia BH1 is currently what scientists call a dormant black hole. It is not actively consuming its companion star. It is not producing the bright X-ray emissions that most previously known black holes produce because they are feeding. It is simply sitting there, in gravitational partnership with its companion, dark and silent and patient. This is precisely why it was invisible for so long. The black holes we discovered before Gaia BH1 were almost all discovered because they were actively feeding, consuming gas and material from a companion star or nearby cloud, heating that material to millions of degrees, producing enormous amounts of X-ray radiation that our telescopes could detect across vast distances. We found them because they were loud. Gaia BH1 is quiet, and quietness, in the context of black holes, is not a comforting quality. It is a concealment strategy, not a deliberate one. Black holes do not have intentions, but the effect is identical to intent. The quiet ones are invisible, and the quiet ones are almost certainly the majority. We have been finding the loud ones for decades. We built entire detection systems around their noise, and in doing so, we created a massive blind spot for every black hole that was not making noise, which, it turns out, is most of them. And this is where things change, because the method that found Gaia BH1 is not based on what the black hole is doing. It is based on what the black hole's gravity is doing to the star orbiting it. The Gaia satellite, launched by the European Space Agency in 2013 with the mission of mapping the positions and motions of billions of stars with extraordinary precision, detected a subtle wobble in the orbit of a Sun-like star in the constellation Ophiuchus. The star was moving in a way that could not be explained by any visible companion. Something was pulling it. Something massive. Something dark. That wobble revealed the presence of Gaia BH1. And the reason this discovery should restructure how you think about the galaxy you live in is this: the Gaia satellite has now mapped the motions of over 1 billion stars. 1 billion. Analysis of that data is ongoing. Gaia BH2 was found in 2023. Astronomers working with Gaia data have stated publicly that they expect to find more. Potentially many more. The data already exists. The black holes are already in it. We just have not finished reading it yet. The galaxy is not what it looked like last week. And it is definitely not what it looked like before 2022. Let's stop moving outward for a moment. Let's move inward instead. Let's go to Gaia BH1 itself. Let's understand what this object actually does to space. Not in abstract terms, not in equations, but in the physical, visceral, immediate reality of what it means to be near something like this. You are in a spacecraft. It is the most advanced human spacecraft ever built. Fully shielded, perfectly powered, carrying every instrument and protection that the pinnacle of human engineering could design. You have been traveling for years. The journey from Earth has taken everything from you. Your muscle mass has degraded, your bone density has dropped, your cardiovascular system has restructured itself around a zero-gravity environment. But you made it. You are here. Outside your forward viewport is a star. It looks almost like our sun, similar size, similar color, slightly orange. It is beautiful in the way that stars are always beautiful when you see them without atmosphere to blur their light. A perfect, hard, unwavering point of intense fire against the absolute black of space. And orbiting that star at roughly the distance Earth orbits our sun is nothing, or rather what looks like nothing. What is in fact the most extreme object within 1,560 light-years of your home planet. You cannot see Gaia BH1 directly. There is nothing to see. No glow, no outline, no visible distortion from this distance. If you did not know exactly where to point your instruments, you would see only the star and the empty space around it. But your instruments know, and they are showing you things that your eyes cannot. The first thing you notice is the gravitational data. Your instruments measure the curvature of space-time around you, and they are reading distortions that increase as you look toward a specific point in the empty space near the star. Space-time is not flat here. It is curved, bent by the presence of 10 solar masses compressed into a 30-kilometer sphere. The curvature is not dramatic at your current distance. You are still thousands of kilometers from the event horizon. But it is measurable, real. The geometry of space itself is different here than anywhere you have ever been. As you move closer, slowly, carefully, instruments measuring every variable, the effects begin to accumulate. Your clocks begin to disagree. This is not a malfunction. This is general relativity working exactly as Einstein described it a century ago. Time runs slower in stronger gravitational fields. The closer you get to Gaia BH1, the more significant the effect becomes. A clock near the event horizon would tick so slowly relative to a clock far away that hours near the black hole would correspond to years further out. You are aging more slowly than anyone on Earth right now. Every second you spend closer to Gaia BH1 is a second during which slightly less time has passed for you than for the people you left behind. Not dramatically less at your current distance, but measurably less, detectably less. The universe is enforcing a different rate of time on you simply because of where you are positioned relative to 10 solar masses. But that's not even the worst part. Light itself is bending around you. Photons, the massless particles that make up all electromagnetic radiation including visible light, follow the curvature of spacetime. They always travel in what are called geodesics, the straightest possible path through curved spacetime. Near Gaia BH1, the curvature is significant enough that light does not travel in straight lines, curves. And this means that what you see around you is not what is actually around you. Stars that appear to be in one direction are actually in a slightly different direction. Objects appear distorted, stretched, multiplied. The black hole bends light traveling past it like an enormous gravitational lens, creating visual effects that have no equivalent in any human experience. If you moved close enough, to a distance of about 45 kilometers from the center, the photon sphere, you would reach a point where light itself can orbit the black hole. Photons traveling at exactly the right angle would circle Gaia BH1 indefinitely, trapped in an eternal orbit. If you were positioned at the photon sphere and looked sideways, you would see the back of your own head. Light from behind you traveling all the way around the black hole and arriving at your eyes from the front. You would see yourself without a mirror, in a circle, in a place where light goes around in a loop forever. And you still have not crossed the event horizon. The event horizon of Gaia BH1 is at approximately 30 kilometers from the center. A sphere 30 kilometers in radius. Inside that sphere, every possible path through spacetime, every direction you could move, every trajectory light could take, leads only inward. There is no outward direction inside the event horizon. The concept of away from the black hole ceases to exist as a navigable direction. Falling toward the singularity is not just inevitable. It is the only thing that time itself can do inside that boundary. This is not metaphor. This is the actual geometry of spacetime inside a black hole's event horizon. The future, all possible futures, point toward the singularity. There is no version of your future that does not end there. Your instruments are screaming. Every system on your spacecraft is telling you to stop, to reverse thrust, to increase distance. But your instruments are also telling you something that your spacecraft cannot compensate for. At the distances you are now operating, the difference in gravitational force between your ship's near side and far side, a difference across a length of perhaps 50 meters, is becoming measurable. This is the beginning of tidal force. The same force that causes tides on Earth, the difference in gravitational pull between one side of the planet and the other, exists here at scales that would tear a spacecraft apart long before the event horizon was reached. The closer you get, the worse the differential becomes. Your ship would be stretched along the axis pointing toward the black hole and compressed along the perpendicular axis. Slowly at first, then faster than any structural material ever engineered could withstand. And you would feel it before the ship failed. The same force acting on the ship acts on your body. There is a point, still outside the event horizon, still technically in the region of space where escape is theoretically possible, where the tidal forces across the length of a human body become lethal, where the difference in gravitational pull between your head and your feet is enough to begin stretching your spinal column, where your blood, which relies on pressure differentials to move, begins to behave abnormally because the pressure gradients across your body are being overridden by something that does not respond to biology. This is what Gaia BH1 does, quietly, invisibly, to anything that comes too close. And it has been doing it 1,560 light-years away, for millions of years, before humans existed, before our sun formed, before our solar system coalesced from gas and dust. This object has been warping spacetime and bending light and creating regions of no return in our cosmic backyard for longer than our planet has existed. We just didn't know. Now let's talk about how we found it. Because the story of the discovery of Gaia BH1 is not just a science story. It is a story about the limits of human perception and the moment those limits were pushed back, and what was revealed on the other side. For most of the history of astronomy, we found things in space by looking at the light they emit. Stars emit light. Galaxies emit light. Nebulae emit light. Hot gas being consumed by black holes emits X-rays. We built increasingly sensitive instruments to collect this light across all wavelengths, and we used those instruments to map what exists out there. This method worked brilliantly. It revealed an extraordinary universe. But it had one catastrophic blind spot. Things that don't emit light. Dark objects, objects that are cold, quiet, and not actively consuming anything, were essentially invisible to every method we had. We knew they must exist. The mathematics of stellar evolution told us that when massive stars die, they leave behind black holes. Given the number of massive stars that have lived and died in the Milky Way over its 13 billion-year history, there should be, as mentioned, somewhere between 100 million and 1 billion stellar mass black holes in our galaxy. We knew they were there. We could not find them. The Gaia satellite changed the equation. Gaia was not designed to find black holes. Its mission was something more fundamental and more ambitious, to measure the positions, distances, and motions of over 1 billion stars in the Milky Way with a precision never before achieved. To build a three-dimensional map of our galaxy accurate enough to show the subtle wobbles in stellar motion caused by the gravitational influence of companions, other stars, planets, or any other massive nearby objects. The technique is called astrometry. It is ancient in concept. Astronomers have been measuring star positions for centuries, but the precision Gaia brought to it was revolutionary. Where previous surveys might measure a star's position to within a few milliarcseconds, Gaia could measure to tens of microseconds of arc. This is a precision improvement so dramatic that it is almost impossible to convey intuitively. It is the equivalent of being able to measure the width of a human hair from a distance of thousands of kilometers. With this precision, something became visible for the first time. stellar wobbles caused by invisible companions. A star orbiting a black hole does not travel in a perfectly straight line across the sky. It curves very slightly, almost imperceptibly, pulled by the gravitational influence of the object it is orbiting. To previous instruments, this wobble was invisible, buried in measurement noise. To Gaia, it was detectable. In 2022, a team of astronomers led by Kareem El-Badri at the Harvard-Smithsonian Center for Astrophysics was analyzing Gaia data when they noticed the wobble in a sun-like star in the constellation Ophiuchus. The star, catalogued simply as a faint background star, was moving in a way that indicated an invisible companion of approximately 10 solar masses. A companion that emitted no detectable light, no X-rays, no radio waves, no infrared signature. A companion that was, by every observational criterion except gravity, not there. El-Badri and his team followed up with ground-based telescopes, measuring the star's radial velocity, the speed at which it moves toward and away from us as it orbits its invisible companion. The measurements were unambiguous. The companion was real. The companion was massive. The companion was dark. Gaia BH1 was announced to the world in November 2022. El-Badri himself described it afterward with a candor that does not get enough attention. When asked what the discovery implied about the number of similar objects in the galaxy, his response was essentially that we should expect many more. The two found so far, Gaia BH1 and Gaia BH2, represent an early sample from what is almost certainly a large and previously entirely hidden population of dormant black holes throughout the Milky Way. But here's the problem. The Gaia satellite has only analyzed a fraction of its total dataset in the years since launch. The full data release, containing positional measurements of over 1 billion stars with the complete precision of the satellite's capabilities, has been rolling out in stages. The analysis of that data for astrometric signatures of unseen companions is ongoing. Teams around the world are working through it right now. The black holes are in the data. We just have not found them all yet. And this is the part of the story that nobody seems to be talking about loudly enough. We have developed, for the first time in human history, a method to detect black holes that are not emitting any radiation. We have confirmed it works by finding two. The data that will reveal dozens more, possibly hundreds more, already exists, collected, stored, being analyzed. We are in the middle of the discovery right now. Not at the beginning of it. Not waiting for it. In it. The map of black holes in our galaxy is being redrawn as you watch this video, and every update to that map makes our galaxy look more populated with invisible extreme objects than the previous version did. What will the final map look like? Nobody knows. And that uncertainty, that gap between the number of black holes we have confirmed and the number we know must be there, is one of the most significant open questions in modern astrophysics. We are not looking for things that might exist. We are counting things that must exist and finding that almost all of them are still hidden. There is a question that lives inside the discovery of Gaia BH1 that nobody asks directly in the news coverage. Scientists know it is there. They discuss it in papers and at conferences and in carefully worded academic language that strips the emotional content from what is actually a profoundly disturbing implication. Let me state it plainly. If the galaxy contains between 100 million and 1 billion stellar mass black holes distributed throughout its volume, and if the Milky Way is roughly 100,000 light-years across with our solar system positioned about 26,000 light-years from the galactic center, then statistical reasoning suggests that there are almost certainly multiple black holes significantly closer to Earth than Gaia BH1. This is not a fringe position. It is what the mathematics of the known black hole population implies when you run the numbers. Gaia BH1 at 1,560 light-years is the closest confirmed black hole. But confirmation requires detection, and detection requires either the object to be making noise or the object to have a visible stellar companion that wobbles in a way that Gaia can measure. What about black holes that are genuinely isolated? No companion star, no infalling gas, no orbital partner to reveal their presence through gravitational wobble. Just a 10 solar mass compressed singularity drifting through the interstellar medium, completely dark, completely silent, with nothing around it to make it visible. These objects, called isolated black holes, are predicted to exist in large numbers. The detection of isolated black holes is extraordinarily difficult precisely because they have no companion to betray them. The only way to detect an isolated black hole is through a phenomenon called gravitational microlensing. When the black hole passes in front of a background star, as seen from Earth, and its gravity bends and brightens the star's light temporarily. This brightening can last from days to years, and if it is accompanied by a measurable deviation in the star's apparent position, it can be attributed to a black hole rather than a less massive object. In 2022, the same year as the Gaia BH1 announcement, a separate team of astronomers announced the first detection of an isolated stellar mass black hole through microlensing. The object, provisionally designated MOA 2011 BLG 191 or OB 110462, was found to be roughly 7 solar masses and located approximately 5,000 light-years from Earth. Again, by cosmic standards, not far. 2 independent methods, 2 separate detections, both within our local galactic neighborhood, both announced in the same year. The pattern is becoming difficult to ignore, and this is where things change in a way that requires you to sit with for a moment. The picture of our galaxy that most people carry in their heads, a beautiful spiral structure with stars and nebulae and open clusters arranged in elegant arms around a central bulge, is missing almost all of its content. The stellar mass black holes alone, if the population estimates are correct, represent a component of our galaxy that is invisible on every star map ever published. They are distributed throughout the same volume of space that contains the stars, woven through the galaxy structure at densities that we are only beginning to calculate, and until 2022 we had confirmed essentially none of them. We have been walking around inside a galaxy of black holes and thinking it was a galaxy of stars. The stars are still there. The stars are real and beautiful, and their light is what you see when you look at the night sky. But the dark component, the invisible population of stellar remnants that we now know must exist but cannot yet fully see, is woven through all of it. And some of those dark objects are close enough that, if our detection methods are correct, they should be revealing themselves in the Gaia data and other surveys within the next few years. But that's not even the worst part, because there is a category of object larger than stellar mass black holes that also lurks in the galactic structure, and the question of how those are distributed is even more unsettling. Intermediate mass black holes, objects with masses between 100 and 100,000 solar masses, filling the gap between stellar black holes and the supermassive monsters at galaxy centers, are theorized to exist but almost completely unconfirmed. We have a few candidates. We have no confirmed detections in the way we have confirmed stellar mass black holes. If they exist, and the theory strongly suggests they should, their detection methods are even more limited than those for stellar mass black holes. And if there are intermediate mass black holes distributed through the Milky Way in numbers that the theory predicts, some of them may also be within our local neighborhood, undetected, unmapped, producing gravitational effects on the stars around them that we have perhaps misattributed to other causes. The map is wrong, not slightly wrong, fundamentally wrong at the level of what is actually in the galaxy we live in, and we are only now slowly beginning to draw the corrected version. Gaia BH1 is 1,560 light-years away. It has a stable orbit and is not moving toward us in any meaningful way. There is no immediate threat from this specific object. I need to be clear about that because honesty is more important than fear that is not warranted. But the discovery of Gaia BH1 opens a question that is legitimate and that scientists genuinely think about. What would it look like if a stellar mass black hole passed through the inner solar system? Not because Gaia BH1 is going to do this, but because the existence of a large population of wandering black holes throughout the galaxy means that the question of close encounters is not hypothetical over the long term. Over billions of years, the probability of a close stellar encounter, and potentially a close black hole encounter, is not zero. Stars in the galaxy move. Our sun moves. Everything is in motion relative to everything else. Over timescales of millions of years, the stars in our local neighborhood cycle through different positions. Astronomers have calculated that a star passes within 1 light-year of our solar system roughly once every 100,000 years. A closer passage, within a few hundred astronomical units, close enough to significantly disturb the outer solar system, occurs on timescales of millions of years. Now apply the same mathematics to black holes. If the black hole population density in our region of the galaxy is consistent with the estimates, one black hole for every few hundred cubic light years, then close passages of black holes past our solar system are not just possible over geological timescales. They are statistically guaranteed over the full 5 billion year remaining lifetime of our Sun. What happens when a stellar mass black hole passes through the inner solar system? The answer is a cascade of gravitational disruption that begins long before the black hole arrives and continues long after it leaves. Months before a hypothetical close passage, gravitational perturbations would begin rippling through the outer solar system. Objects in the Oort cloud, the vast sphere of comets that surrounds our solar system at distances of up to 100,000 astronomical units, would be nudged out of their stable orbits. Thousands of comets would begin falling inward toward the Sun. Over the following years and decades, the inner solar system would receive an enhanced bombardment from these objects, comets arriving in quantities far beyond the normal background rate. As the black hole moved closer, within a few astronomical units, the effects would accelerate dramatically. The orbital paths of the outer planets would begin to shift. Jupiter, the planet whose gravity currently acts as a deflector shield for the inner solar system, capturing or ejecting incoming objects before they can reach Earth, would be tugged. This orbit would change. Its protective influence would be compromised. At the closest approach, assuming the black hole passed at a distance of, say, 1 astronomical unit, roughly Earth's distance from the Sun, the gravitational interaction would be catastrophic on a geological scale. Planetary orbits would be permanently altered. The stability of the inner solar system, the carefully balanced gravitational dance that has kept Earth at a livable distance from the Sun for 4.5 billion years, would be disrupted. Earth could be flung to a wider orbit, a narrower orbit, or ejected from the solar system entirely. A world ejected from its star. A rogue planet, cooling slowly in the interstellar dark, retaining whatever heat its interior could hold. The surface freezing within decades, the oceans turning to ice over centuries, the atmosphere liquefying and falling as snow over millennia. No sun, no warmth, no photosynthesis, no surface life. Whatever survived underground around hydrothermal vents in the deep rock, those would be the last living things on a planet that had been a garden for billions of years. This is not science fiction. This is the mathematically predictable outcome of a close black hole passage through a solar system like ours. The specifics would depend entirely on the distance and speed of the encounter. But the mechanism is real, the physics is well understood, and the only reason it has not happened yet is probabilistic luck distributed across billions of years. But here's the problem. We would not see it coming. An isolated black hole, the category most likely to make such a passage because they are unbound from any star, is dark. It does not emit light. It does not emit radio waves. Its only detectable signature is gravitational, and our gravitational detection methods are currently nowhere near sensitive enough to detect a stellar mass black hole on an approach trajectory until it was already extremely close. How close? The estimates vary, but some models suggest that a dark, isolated stellar mass black hole approaching on a trajectory toward our solar system would only become detectable through its gravitational microlensing effect on background stars when it was already within a few hundred light years. At typical stellar velocities, tens of kilometers per second, that detection window might give us hundreds of thousands of years of warning. Or it might give us far less, depending on approach angle and speed. That sounds like a lot of time, until you remember that we currently have no monitoring system specifically designed to detect approaching dark objects. No dedicated survey, no early warning network. The Gaia satellite revealed Gaia BH1 and Gaia BH2 as a byproduct of its stellar mapping mission, not as the result of a system designed to detect incoming threats. We have asteroid monitoring programs. We have comet tracking. We do not have a black hole early warning system. It has never been built because until very recently the idea of a black hole close enough to pose any threat in human or even civilizational timescales seemed remote enough to be comfortably deprioritized. The discovery of Gaia BH1 in 2022 did not change the immediate threat calculus. But it did something subtler and perhaps more important. It demonstrated that our census of nearby dark objects was wrong in a way we had never properly quantified. We thought we knew what was close to us. We were wrong about black holes specifically because we were looking for them the wrong way. And the correct question to ask after any discovery that reveals a gap in our knowledge is not, does this specific thing threaten us? It is, what else might be out there that we are also looking for in the wrong way? Let's zoom out one final time, not to make this smaller, to make it correctly sized. You live in a galaxy called the Milky Way. It is a barred spiral galaxy approximately 100,000 light-years across, containing somewhere between 100 billion and 400 billion stars. For most of human history and for most of the history of astronomy, the galaxy meant the stars, the visible things, the things that emitted light and could be seen and mapped and catalogued. But the visible stars are not most of what is in the galaxy. The dark matter that holds the galaxy together, the invisible gravitational scaffolding that keeps the spiral arms from flying apart as the galaxy rotates, is estimated to outweigh all the visible matter in the galaxy by a factor of roughly 6 to 1. 6 times as much dark matter as stars, gas, and everything else combined. We cannot see it. We cannot detect it directly. We only know it is there because without it the galaxy would not rotate the way it does. Then there is the dark gas and dust, clouds of cold molecular hydrogen and other compounds that do not emit visible light and are only detectable in specific wavelengths that require specialized instruments. These clouds are vast and numerous, and they contain the raw material for future star formation. And then there are the black holes, the stellar remnants, the neutron stars, the white dwarfs, the failed stars, the rogue planets ejected from their solar systems over the galaxy's history. All the dark, quiet, invisible objects distributed throughout the galaxy's volume. Some of them extreme, some of them merely dark, all of them absent from the maps that human civilization built of the sky above it. The galaxy that you actually live in, the true Milky Way with all its contents accounted for, is almost nothing like the image on the poster. The spiral arms of bright stars are a small, luminous fraction of a much larger, much darker, much more densely populated structure. We have been mapping the poster version. The real version has been there all along, in the dark, waiting to be found by instruments precise enough to detect it. Gaia BH1 was the first confirmed member of this hidden population in our immediate cosmic neighborhood. It will not be the last. Within the next 5 to 10 years, as Gaia's full dataset is analyzed and as next-generation observatories come online, the Vera Rubin Observatory, the Nancy Grace Roman Space Telescope, the Square Kilometer Array Radio Telescope, our picture of the local black hole population is going to be revised dramatically. The number of confirmed nearby black holes is almost certain to increase. The distance to the nearest confirmed black hole from Earth is almost certain to decrease. We may be moving toward a reality in which we know of confirmed black holes not 1,560 light-years away, not 500 light-years away, but 100 light-years away, 50 light-years, distances that would have seemed unthinkable a decade ago. Still not dangerous, still cosmically remote in human terms, but close enough to force a new kind of awareness of what the neighborhood actually contains. We are not alone in this galaxy. Not because of alien life, that question remains open, but because the galaxy is filled with objects that our mapping has been systematically missing. Objects that were there before our sun formed. Objects that will be there after our sun dies. Objects that are woven through the same volume of space that we have been living in, charting, and calling home, while being completely invisible to every survey we built until 2022. There is a question at the center of all of this that I want to leave you with. Not because there is a satisfying answer, but because the absence of a satisfying answer is itself the most honest thing I can give you. Gaia BH1 is 1,560 light-years away. We found it in 2022. We found it because a satellite designed to map star positions detected a stellar wobble that revealed an invisible companion. That is a profoundly specific set of conditions: a visible companion star, a detection satellite with sufficient precision, and a team of astronomers who recognized what the data was showing. How many of the black holes that must exist in our galaxy are currently undetectable under any conditions we can currently create? How many are isolated, no companion star, no infalling gas, no stellar background close enough to produce a detectable lensing event? How many are in regions of the galaxy where our current surveys have insufficient coverage? The honest answer is we do not know. The gap between the few dozen confirmed stellar mass black holes and the 100 million to 1 billion that theory predicts must exist is so vast that even optimistic projections for the next generation of surveys leave the vast majority of the population undetected. We are counting in ones and twos what exists in the hundreds of millions. This is not a failure of astronomy. It is a statement about the fundamental difficulty of finding things that are designed by physics to be invisible. Black holes do not violate any law. They do not conceal themselves through any active mechanism. They simply occupy the extreme end of a spectrum that runs from things that shout their presence across the galaxy to things that make no noise at all. We built our detection systems around the shouting ones and called the universe mapped. Gaia BH1 reminded us that the map had a massive blank section where we had written nothing simply because we had nothing to write. Not because nothing was there. Look at the sky tonight. Find the constellation Ophiuchus. It sits on the celestial equator, between Scorpius and Sagittarius, visible from most of the world in summer. Inside that constellation, so faint it requires a telescope to see, is a sun-like star that orbits a black hole every 186 days. That star has been making that orbit for millions of years. That black hole has been sitting in that patch of sky, curving space-time, bending light, creating a region of no return, for longer than our species has existed. And we looked at that patch of sky every clear night for the entire history of human astronomy and saw nothing unusual. We called that patch of sky empty. It was not empty. It was never empty. We simply did not yet have the tools to read what was written there. And if that one small patch of sky contained a secret that size, what are the other patches hiding? Every one of those points of light you see tonight is surrounded by darkness. And we have now learned, confirmed, measured, published, that some of that darkness is not empty. Some of it is waiting, not for us, not with any intention, not with any awareness of our existence. Black holes do not wait. They do not watch. They do not care. But they are there, 1,560 light-years from where you are standing, probably closer, in directions we have not yet looked with the right instruments. In the galaxy we have lived in for our entire existence as a species. The universe did not become more dangerous on the day Gaia BH1 was announced. It was already exactly as dangerous as it turned out to be. The announcement simply moved the danger from the category of theoretical to the category of confirmed. And what it confirmed is this: the galaxy we mapped was always a simplified version of the galaxy we actually live in. A version with most of the dark things removed because we could not see them. A version that felt comprehensible and navigable and, in its own way, safe. The real version is darker, more densely populated with extreme objects, more threaded with invisible singularities than we accounted for. Not safer than we thought. The actual probabilities of danger are unchanged, but stranger, more honest, more accurate to what was always actually there. The night sky did not change in 2022. Our understanding of what was in it did. And once you know what is in it, once you understand that the empty-looking patch of sky contains a black hole and that the methods to find other black holes are only now being developed and that the census of nearby extreme objects is almost certainly going to be revised significantly upward in the coming decade, you cannot quite look at the sky the same way again. It is still beautiful. It is still the same stars your ancestors named and watched and navigated by. The light is still the same light. The constellations hold their shapes. But the darkness between the lights is deeper than it looked before, and more occupied. And we are, finally, for the first time, learning how to read what is written there. And we are only at the beginning. Whatever we find next, it is already there. It has always been there. We are simply the first generation with eyes sharp enough to begin to see it. And what we see is going to change everything we thought we knew about what surrounds us. The universe is not empty. It never was. Subscribe, because what we find next in that data will be its own video entirely.